Thank you. Good morning to you too. So just to remind ourselves about what we're discussing iterators, which is a way of abstracting a traversal or moving through all the elements within a collection. So the idea of scanning through all of them, it should be independent of whatever particular implementation of a collection that we're busy on. We had said that we could think of it as an ADT that now allows us not only like position to access a particular element at a place within a list, but now to also search through or scan through that list by being able to check, or that particular ADT by being able to check, do we have a next element within this traversal, this walkthrough of this particular, of the elements within this ADT, and move on to that one by using next. Right. And there were some questions or some confusion between the two terms that we were using. The one was iterable, the class is iterable, that allows us to scan through all the elements within it, and that of iterator. Let me just move to, I believe this was the very next slide that we're about to go through, or that we're busy on. So Java util has two interfaces. The one is iterator, and that one simply says that you should have a method iterator that returns a type of iterator, and the iterator type itself, the iterator type itself simply has a few methods that ensure that we're able to scan through that particular structure, and that is simply having that ability to access the particular place we're in, the ability to check, is there a next place, and be able to move into that using next. So those methods. Now, for us to say that a data structure is iterable, that means that it has a method iterator that returns an iterator. So we know exactly what iterator does. It simply gives us the ability to access the current place that we're at in this traversal, to be able to check, is there a next place, and to move on to that next place. And that's exactly what needs to be returned for a method iterator. If an ADT or data structure in general has that iterator method, then it is iterable. All right, and that iterable interface simply says that if this particular data structure that we're working with implements iterable, then it has a method iterator that can return an iterator over that data structure to us. We discussed a bit that it's very useful for each loop, that if we are, in fact, I'm sure you have been asked this kind of question in Comp Sci 2, that when would you use a regular for loop where we use some index and we check that it first starts with some initialized value and stays less than some bound, and that we change the value of each time we iterate through our for loop, when we use that regular for loop, and when we use a for each loop. Do you still remember what the answer to that question would be? All right, so the question, there's a question already. So with iterator, it is not forced to have iterable. That's exactly what it does for. If you say this type implements iterable, then it must have a method iterator that will return to us when we call it an iterator over that data structure. Right? I would like us to remember, when would we use a for loop and when would we use a for each loop? Okay, for each loop to traverse through a collection, true, but certainly we could use a regular for loop to do that. Of unknown size, okay, I'll allow that one. A little more specific. For each loop, we have no defined index of the collection. Exactly right. I believe that is what you taught, that you can't use an index to do that traversal, right? So if it was like an array, then great. You'd want to use a regular for loop because you'll be using that index to actually traverse over that entire data structure. When you don't have that, then you'd rather use the for each loop because you're not going to do anything with that particular index within that for loop. A couple of answers for next loop. To be able to modify and read, well, actually within the for next, oh yes, for next, yes, that one, yes, would be able to modify, whereas within the for each, we can access the elements within this particular data structure, but we can't actually change them. Then we use a for loop when we want to change the elements. All right, so good, we do understand what the differences are, which is great. And usually we'll simply create another class that can that implements iterator. So it implements the methods that define within iterator, and we'll return an object of that type that contains the elements of our particular data structure with that method iterator. All right, so for it to be iterable, it has to return an iterator. We really define an iterator in a separate class because they're closely associated. This is usually a nested class. And so we will use that, create an object of that type, and return it when we call the method iterator within our iterable class. Right, so our for each loop, we should know what that looks like. We'll usually have a variable of some type that we define, and then an expression that equates to some data structure. And this allows us then to use that name to access the elements within that data structure. Right, and we have an example there. We have an array list of type integer, which we call values. Then we want to access the values. We want to access those values to actually be able to sum up all those values. We have there for integer I, that's the type that we're dealing with, type big integer, and values, so that'll give us all the integers contained within values. And then we want to say sum plus equals I. So the question is the statement allowed? Simple yes or no, what do we think? Is this statement allowed or is it not allowed? Yes, yes, yes. Yes, we're not changing the elements that we're accessing. We're simply taking them and adding them to this variable sum, so we are allowed to do that. Right, if instead we were to try and change those, we know that within a for each loop, we're not allowed to do that, so that wouldn't work. But here we're simply taking them and each time adding them to this variable sum, and we should at the end of it then have the sum of all the values over this particular data structure. So what are the kind of ways that we could implement this? So an array is a nice simple way to do this. What would we actually be doing on the back end? So each time that you call that has next or next, well, our idea of a cursor here that tells us the place we're at and allows us to advance that cursor to go to the next place. And of course, also check that there is a next place for us to go to before we do that. Would simply be using our index to do that. So our index would keep track of where we are. We could increment the index, right, without actually exposing that to the code that's using this particular iterator. But we would increment that or even check what is at 1 plus that index to be able to check, is there a next place within this particular iterator or moving this traversal that we're going through? And can we actually then go to that? We could also use a W-linked list. Should be comfortable with that idea. We have our Sentinel nodes, our header and our trailer, we have our list within that. We could then use a reference pointer to a particular node P. We know that we're able to return the element that is stored at that. Because we also store a reference to the next one, we would be able to go on to that. All right, question, last part had to go. Okay, did you miss anything important? Up to this point, we really just have been reiterating what we discussed last time. So we're on the same page when it comes to the terms iterator and iterable. All right, we said that that iterator is simply an extension of the idea of a position. We can access a particular element in a place within a collection. We can also now check, is there a next one and go on to that next one. That defines an iterator. For a data structure to be iterable, or data type in general to be iterable, it has to have a method iterator that returns to us an iterator over that data structure. Right. So for the linked list version, we'd use a W linked list. That's convenient for us. We would then use a reference to a particular position to keep track of where we are. So that will be our cursor in this case. We can check if there is something that comes next simply by checking that it's not equal to our trailer. And if that's the case, then we can then link hop to go to the next one. Granted, we actually have to expose nodes in this particular case, not just positions, but we can do that. Right, so we can now add methods to our existing ADTs, all the ones we've discussed thus far, to be able to make them iterable. Right, and that means that we can then use a for each loop on these. Because when we call them within that for each loop, then an iterator over them will be returned to us, and we can simply scan through all those elements that were contained within our original ADT. Right, we have a question: which would be the cost-effective / easier implementation? Right, well, what do we know about the between an array and an ADT? The array is of a fixed size, so if we know a priori beforehand what's the maximum size of elements that we're dealing with, then the array could work. Granted, the array always uses order big N amount of space, so the size of that space, or rather capacity of that space, is always used, regardless of how many elements are actually within that array. So if space is a concern, then the array would not be the best way to go. If being able to easily index into a particular place within this list and then be able to increment is what's of most importance, which it really isn't, then the array would be preferable. In terms of simplicity, I would say the array is certainly simpler. It is a Java intrinsic, it's already there for you, but we realize that it has that restriction of fixed capacity. Granted, we talked about how we can get around that and create a global array, but we're wasting, on average, order n each time that we're inserting if we are using our incremental strategy, where we add a certain amount of blocks each time, a fixed size, or our doubling strategy. Overall, we're wasting order n time. All right, so we should understand the differences. It really depends on whether or not we know how many elements, the maximum amount of elements that we're going to deal with. So Java has a list iterator ADT. It has a little more than what we discussed in our iterator ADT. So it does allow you to access the current position, check if there is a next, and actually then move on to that next, but it actually allows you to move in both directions. So our definition of an iterator says that allows you to scan once through a collection. So Java's list iterator actually has a little more than that, allows you to scan in both directions. And so it have to also have has previous and previous to actually go on to that one. Also allows you to set, so to replace what's at a particular place as you're going through your scanning through these elements, and to remove as well. Remember that we said that these fail safe in Java. So just note that you can call iterator more than once. So you can have more than one iterator over a particular collection. But if any one of them changes the values of the elements that it is scanning through, then the other ones will fail. And as we've already said, if the original data structure changes its elements, then all of the iterators over it will fail. All right, in Java, that's what we do to make sure that you're not actually trying to access and change the bigger issue. Elements at the same place using different iterators, we wouldn't know what the end value should be there. Right, so it is making sure that this works correctly when working like in a month. So it should work in a thread safe manner. So if we have multiple threads and we're executing things at the same time, we have to have the case that, I don't know how much you guys have worked with multi-threading, I think you have, but in second year, but that even when things are done at the same time, it should equate to a sequential execution of things in a linear fashion. And so to be thread safe, we should, if one changes its values, the other should stop working. If the ADT itself or the data structure itself changes its values, all iterators over it will stop working. Good. What if we want to iterate through your ADT and change data that they contain while we are at it. All right. Well, our rule, or rather in Java, we said that Java uses that snapshot approach. So it gives you what the values are at a particular moment. Yes, you can change what those elements are within your traversal. But if you change the things within the data structure itself, that iterator is no longer valid. And of course, if you have multiple ones, you change one of them, the others aren't valid. So if you want to change the particular values, you'd have to make sure that you don't have multiple iterators over that. You'd have a single one, and that one would be able to change those things. Right. But as we said, the Java library one allows you to do a little more, move in both directions, be actually able to set and remove things as well. In general, the remove method actually is kind of described, you could say, as part of the iterator interface. However, it's optional, so you don't actually have to implement remove, right? But it is described within that Java util iterator as well. That's interesting to note. Right. So a position iterator or position iterator would return to us then a collection of positions containing the elements that we have in our collection. We could create then that positions method that will return to us an iterable objects for all the positions contained within our particular collection. This particular object then has a method iterator, so it can return to us an iterator over those positions, which can be called to return an iterator on the elements. The list iterator in Java, as we already said, invalidates on update for multiple iterators, and more so, we also said that if the data structure itself changes, that also then invalidates all the iterators over it. So, how is implementing this iterator interface any different from what we were doing originally? Well, up to this point, we haven't said that you have to have a systematic way of being able to step through all the elements within this collection. Granted, thus far we've only been dealing with linear, with collections, so with lists in general, which all have a linear order. So it's simple enough to see how we would do that. However, in our very next ADT, we're going to be talking about, so not this one, but the next chapter, we're going to be talking about trees, which don't have a linear order. So there, if we wanted to step through all the elements within that, there wouldn't be a straightforward way for us to do that, unless, of course, we have an iterator, which would return to us, regardless of whatever implementations, array or linked list, but a simple way to be able to step through all the elements contained within that tree. So right now, it seems simple. It seems like we could already do that quite simply. However, we'll see that with our other data structures that we discussed, you can't easily do that. All right. So the last thing that we're going to discuss is really a general purpose ADT. It's called a sequence. It allows us to be able to access elements in both ways that we've discussed for these derivative types of lists. So we talked about the array list, which is an index list, so that adds the idea of an index to a list. Then we talked about a positional list. The one allows us to be able to describe places in a list using an index, right? We said by definition, that's the number of elements that occur before a particular place. Then we said the other one uses positions, which have a relative idea of order. They don't change if elements are added or taken away before that. In fact, even if we don't change the particular element stored at the specific position that we're keeping track of, only if we remove it and that way destroy the position. So this one allows us to be able to access elements in both ways, using indices, but also using positions. So clearly, it uses multiple inheritance, right? Both of our ADTs, which are descriptions of behavior, which in Java would be realized using interfaces, this would then implement both those interfaces, so it has to have all the methods that each of the ones we've described to this point have. To be able to access and change things using indices, and to be able to do the same using position. So we could, again, implement this with an array. We can also implement with linked list, and we'll look at those two different things. So this sequence ADT is a union of an array list and a positional list. We can access these elements using index and position. It still has generic methods or the helper methods, size and is empty. And it has the array list based methods, get I. So we give it an index, it should return to us the element that's stored at that particular index. We can set IO, so we can take a new object and replace whatever was contained at index I or what was at the place with index I. Add IO, which we said will actually insert it into there and move everything else to the right as necessary. If it happens to be at the end of our list, then it simply adds at the end of our list. And remove I, which removes that which was at index I, and then has to update all the indices after that because they will now have one less value, right? The value of one less. Those we are familiar with, but now it has to also have our position-based ones. So we have to be able to call first and return what the first element in our list is. Last as well does similar thing, but for the last element in our list, given a reference to a position P, we should be able to return the position before that using previous, and the position after that using next. Replace P, so replace with that position P with this new object O, add before and add after, add first and add last, and remove P. So we'll come to all those because we started discussing those when we started discussing the list. But we have to be able to access and change things within our sequence using all of these as well as those of the indices. Then we have two bridge methods that allow us to be able to, given an index, return a position, and given a reference to position, return the index of that particular position. So at index I, we'll return to you the position that it has index I. Index of P will tell you, if you have reference to P, what is the index of P within our list. Right? Granted, we call it a sequence now because it does that multiple inheritance. All right, so what can we use this for? Well, all the things that we've discussed thus far, we can use it in FIFO fashion, in LIFO fashion. We could actually use it as simply a general purpose ADT for storing elements in this linear structure. Some direct applications will be, we'll replace them for all the things we've discussed thus far. Right? We could use it for a small database. So we could easily scan through it using a cursor. It would work for a small database. Indirect ones, as always, we could use it as part of some more complex data structure. So if we implemented this with a linked list, we could use a W linked list, right? Because that would make it a lot easier for us to do things like previous and insert before. So we could use our W linked list. That would be a reasonable implementation of sequence ADT. However, we also have to keep track of our indices now. Or rather, when we call those methods using our indices, we won't be able to just index into it. We'd have to do our link hopping to be able to get to the elements stored at a particular index. So our nodes would now be our positions as before. They store an element. They allow us to be able to retrieve what's at that element and access the links to the previous node and the next node. Again, we'll have our two sentinel nodes that make it easier to implement all our methods. So this is what that would look like. Looks like our normal W linked list. We have objects of the same type. We store two references, one to the node before and the node after. So we know that our position-based methods all run in constant time. We can access first and last, we can insert before and after, we can add first and add last, we can remove the particular position by pulling out that node. All of those are constant time. They don't depend on the number of elements stored within our W linked list. However, the index-based methods will actually require us to begin either at the beginning or the end of our list. So if we know that our index is actually past the halfway mark, we could start at the end of our list and then hop backwards. So these actually, the index-based ones will require us to start at the beginning or end of our list and then actually link hop the number of times that we have to hop to be able to get to a particular index. And so these will run in linear time. Even if we're being smart and we start out at the beginning or the end, which makes it at worst n/2 hops that we have to make, that is still linear time. All right. So there's no way to get around that because we can't actually index into a particular position within that list. If we're using our array-based one, well, we said that if we use a circular array, so using that modular arithmetic, then we could be able to do some things in constant time, like adding things to the front and adding things to the back. However, now, because we're doing that, we'll have to keep track of what the index of a particular element is within our array. So we'll be storing not just the element itself, but also the index of that. Again, updating it as necessary as we remove and add things before that particular element. So we have indices F and L, which keep track of what's the first position within our list, what's the last one. Remember, those will be changed using modular arithmetic to make sure those wrap around. And we know how that works. What would that look like? Here we have our array. Within each array, we have a reference to the objects that are stored within our list. However, instead of just keeping a reference to that object, we also keep track of what the index now within our sequence is. So if we were to insert something at the front, we realize that the indices of all the other ones would have to be incremented by 1. If we remove something, then we realize that the indices of all the others have to be decremented. Right. Because we're using the circular faction, we can easily add things at the front and the back, allowing to move things over. However, we will still have to, if we're adding things or removing things from the front, make sure that we change the indices to keep that correct. Make sure that those actually represent the number of elements that occur before that particular one. Right. So if we're using an array, then we can still easily index into that, right? Because we simply then index into our array at F plus the particular index that we're working at. So we can still do things like set I, E in constant time. Our add first and add last would be done in constant time. That's pretty straightforward. Our size and identity for both of these will be in constant time. However, just see that the ones that depend on indices, if we're using our doubly linked list, would not work in constant time. So for example, at index, index of, and get I, those would all take linear time within our list. Set IE, that would also take linear time. If we're adding or moving at a particular index, that will also take linear time. And the ones that actually require us to add things arbitrarily within our list, those would then take a certain amount of shifts within our array. So that would also take linear time within the array. And if we're adding before, add after, that will also take up to n moves. So that would take linear time as well. All right. The advantages and disadvantages, the ones that use indices will be constant time within our array. However, those that require us to change indices will be linear time. Within our list, those that are simply adding things before or after a position, doesn't change the position, that would remain constant time. However, those that use indices would then take linear time. All right, so in this case, we could say you can choose which implementation you want to use, but it works well as general purpose ADT that allows us to be able to move things around, or rather allows us to be able to represent any of the ADTs that we've worked with thus far. All right, so the question, why isn't remove I constant time? Well, remember that if we're removing at a particular index, not the first or last, this one will then require us to update all of the things in the list that occur after it, because they all now have one less, their index has a value of one less than before. Because an index says how many elements occur before this. So if it's somewhere between, in the middle of our list, everything that occurs after it has to then have its index changed. Okay, I trust that makes sense. Right, and then there's a case study of how we could use a sequence, what it may be useful for. I don't believe this is actually in the new text, but it certainly is in the older text. And it simply tells us, well, what could we use this type of data structure for? So a general list. What could we use a list for? An example of that is a favorites list. So think of when you open a new tab in Firefox, I'm sure Chrome does similar behavior. It shows you the top X sites that you visit each time. I think it's about 8 on Firefox. So these are the top websites that you visit each time that you open your browser. Well, how does it keep track of those particular things? What are the different ways that we could keep track of what are the top X websites that you visit each time that you are busy in your web browser? So that would be what we call a favorites list, right? So each time that you access the same website, we should actually increment how many times it's been accessed. And then if we take the top X entries, so let's say we're sticking to the idea of in Firefox, if we take the top 8 entries that we store within this list, as in the ones that have the 8 highest counts, then we're able to return to you that favorites list. So one way we could do this is simply each time that you visit a new website, we add that to our list. If it isn't already in there, then we add it to our list with a count of 1. Each time that we visit a site, we go through our entire list. If it's in that list, then we simply increment the count by 1. If not, then we add it to that list and give it a count of 1. By doing this, then, we keep track of how many times you're visiting different sites. We could keep this in order of decreasing values. That would make it really simple for us to actually remove or return our top 8. We'd simply go to the first 8 elements within our list, and that would allow us to display it very easily. Right, so regardless of the size of our list, it would take us the same amount of time. It would take us 8 accesses to return our favorites list. So that would be pretty useful. However, we realize that each time you visit a new site, you'd have to scan through the entire list to increment the count of that website. Not so great. So each time that you visit a new site, it'd be linear time to actually increment whichever particular site that is. If it didn't exist, then we simply add it to the end of our list. It's still linear time. However, to return what the top 8 are would be constant time. Another way of doing this that turns out to be quicker in certain cases is to each time that you access a site, move it to the very front of our list. Now the question is, why would this work? And there's this idea of the principle of locality. And in fact, it's the same reason why when you access a space in your secondary memory, and so on your machine, you access some data on your hard drive. It's the reason, or rather, so it's on your hard drive, you copy into memory, but then when you actually want to work with it, it's copied into cache. Why is it that we copy an entire cache line and put that within our cache instead of just using it once and throwing it away? Well, the idea is that once we access something, we are likely to access that same thing in the near future. So you're likely to access the same thing again right after that. This is the principle of locality. And in fact, when we're working with things that are stored in memory, you're often likely to access things right after that. That's why you copy the entire cache line. So here we're using the idea that when you access a site, you are likely to access that same site again. And so in that case, each time that you access that site, you access the same site multiple times, it will be at the very front of your list. So now you'd be able to, in constant time, increment that particular count of that website. Right? Conditions being true that you actually do tend to do this, but it is a heuristic, it is a rule of thumb that often works. And so if we use this particular approach, there is some calculation of this within the text that shows us that if we were to use the linear ordering, so that way we store our counts in decreasing order, then it would take us a visual order n cubed time to add n different, to access all our sites n times. Whereas if we're using this move to front heuristic, this move to front rule of thumb, then it would take us n cubed time. So it would be quadratic time instead of cubic time if we were to use this heuristic. It doesn't always work certainly, but if we act in this manner, which people often do, when you access something, you're likely to access it again after that, then this move to front heuristic works quite well. We just have to note that there's a trade-off here. If we are keeping them in order of decreasing counts, then we can very easily in constant time recover or display those 8 most popular sites. Where if you're using the move to front heuristic, then they're not going to be in order. And so we'll actually have to, in n squared time, be able to return these top 8. Why? Because each time we're going to look for the max and remove it, okay, actually would copy what we have in our favorites list to a new temporary list, then scan through that, find its max. That would give us the first one. Scan through the entire thing again, find the current max, remove that, that gives the second one, do that 8 times, and that would give us our top 8 thing. So it would now take n squared time to actually be able to return n things from that list. So there is some trade-off between either how easy it is for us to retrieve the top 8 in our case, or how easy it is to increment the counts of these as we visit them. Right, and we could do all this using a list and also a temporary list in the case of the move to front one to be able to return however many maxes we want. Right, so that's an example of what we could do with a list. So our discussion of this and there, we certainly do use them in the manner that was discussed, though as part of more complex data structures. And we'll see that presently with our discussion of trees. If there's any confusion or questions, please put them in now while I switch to our next lecture. Right, yeah. So for the mini project, we need to wait for feedback for our proposal, or can we start coding our solutions now? You can start coding the solution now. As I said, we intended to have them back to you within a week. However, in marking those that have been marked thus far, we saw that the issues that you have are kind of nuanced, that most of you understand what a blockchain is, but not all of you understand that we're actually trying to solve more than one problem. There is the problem of, well, making a list that's resistant to retroactive change, right? And hashing the data within a block, and then in the next block storing that previous hash and the hash of that block, and the next block storing the previous hash and hash of that block. Sure, that means that you can't change one thing without changing anything that comes after it. I think you understand that. I think the fact that you do gave you a good understanding of that. However, that isn't enough to solve all the issues that are there. Because what about the fact that you could have a malicious node within your network that wants to intentionally add new invalid blocks to your blockchain? How do you solve that? Right? The high-level discussion of that is that you have to add some system of punishment and reward. And if we're talking about Bitcoin as an example, granted you're not allowed to do cryptocurrencies, but that's an example that you should be familiar with, then the process of actually mining, which is solving some cryptographic problems that take a significant amount of computing time and thus energy, would be the punishment for coming up with a new block. The reward would be to be given coins. And if we find that you created an invalid block, then you would lose the reward that you were given. So there's a punishment of work that has to be done, right? And yes, some of you, quite a few of you understand that. You talked about different proof of work algorithms, so different ways to prove that you've actually are incentivized to do the correct work. However, that means that there has to be some work that costs time that you have to do. Granted, there are some other approaches to this. If you discuss that, that's fine. So proof of stake or some of the other ones, they could use those as well. But there has to be some system where you're doing some work, and then the other nodes in the network, or a certain amount of other nodes in the network, are doing work to check that you did your work correctly. Right, so in Bitcoin, it's doing that cryptographic work that actually demands a certain amount, and in the case of Bitcoin, a significant amount of computing power and energy. Then if you win, if you're the first one to solve that problem and can add the next block, everybody else switches from trying to compete with you to trying to check your work. And their incentive for checking the work is that if they find that you did it wrong, then they get the reward that you were supposed to get. So they are actually incentivized to be very strict in checking your work. And it should be something that is labor intensive for the person who is trying to solve that problem first, but not labor intensive for those that are trying to check it. And so the work that's done is to find a particular type of hash that has, I think, 13 leading zeros. But the hash that the ones that are checking the work have to do is a lot simpler. It's like a good hash. It is not computationally expensive, and it's rather fast. And so they can do not the same work, but easy work to check that the other ones, the one that won the competition to create the next block, has done its work correctly. Point being, there has to be that cost and that reward to keep people adhering to the rules, to adding valid blocks and for the other ones to check that those blocks are valid. So to simply say in general, we use a hash. It's what I had in the previous prac, or the one before that one, is too simple, right? And as I said, that hash chain was a very watered down version of what you would do within a blockchain to store data. And that would work for things like uTorrent, for things where you're simply trying to check that there hasn't been some change in the data as it was sent from one user to another user, but not enough for the idea of a blockchain. And so because Prof. Anwar picked that up and in our discussion, we decided that we were not going to have assistants marking those. It'll just be he and I. And so instead of having 12 people, we only have 2, so it is going to take a little longer. And simply because the idea of the project is more nuanced, and it seems that even where you are having issues, it's that there's a partial understanding of what the problem is, right? And we'll tell you in that case that, well, you need to add some proof of work to this, or if it's that you are storing the incorrect data, well, you need to store this additional data. Feedback will hopefully is succinct, but will help you to understand what you did incorrectly. There's a question, what would cause our idea to be rejected? Well, thus far, the ones that were outright rejected, as in got less than 3, are those where people talked about general things. So people were like, okay, there is such a thing as proof of work. I can add nodes, but you weren't talking about how your problem could be solved by storing specific data from your use case within blocks, creating a blockchain, and then having some way of vetting new blocks. So if you simply paste the things that you got from the internet, rather than actually saying how you're using a blockchain to solve this problem, then those will be flat out rejected. The others, if it was a lack of sufficient information about what you're doing, would usually get a 3. 4 if you could have done better, and then 5 if you have enough and your problem is described in such a way that we understand you will be able to solve this using a blockchain, right? And in that case, we would tell you, well, this isn't enough, you need to do some others. You need to do a little more work. You wouldn't need to resubmit, you would simply understand what is lacking and what you need to add to your project. So vetting means each block must do proof of work. No, vetting means that when you have created a new block, the network is able to check that what you created was a valid block. And that system of, if we're talking about proof of work, then that system of punishment and reward, where you have to spend a certain amount of resources to be able to create a new block, and you are rewarded with something, in that case, some coins in Bitcoin, and then the others are incentivized to check your work, and they're rewarded in the form that if they find that you did your work incorrectly, then they get that reward instead of you. Right? But that is a simple, that is one example. Right. We will see on Eve whether ideas. Yes, you'll see on Eve what your mark was out of 5, and a comment that tells you why it is you got that mark. Right, but unfortunately, because of the issues that we picked up, it will take a little longer because we're not going to use the assistance that we had that we intended to initially. When will we get marks for Prac 4? As always, you should get them by Wednesday at 12 noon. If you don't get them by that time, please send me an email. We'll check on your assistant. But thus far, they are available each week by 12 noon on a Wednesday. Right. Thank you for asking that question now, because I know if we had asked it right away at the beginning, then we'd be asked the same question over and over. Right. So the next entity that we want to discuss is a tree. Really going to go through this nice and slowly because there are some new ideas within this. And please, nowadays, really important that if there's something you understand, that you ask the question, and we certainly have the time to repeat what has been said to make sure that we're all on the same page. Right. So a tree, you can think of it as like a top-down chart. It's an abstract model of a hierarchical structure. Think of hierarchical structures that we've discussed before. In Infos 2B, we talked about monolithic or hierarchical organized organizations, those that have that top-down control. So you have some executives at the top, then some middle management, then the frontline workers at the bottom. You have this organization, then departments within that, then perhaps some sub-departments, then employees with a top-down system of control, right? So it could be used to represent something like that. Really can be used to represent anything that has a hierarchical structure. So an organization is one example of that. And we'll see an example of an organizational chart. It can also be used to represent a file system. Just think of your file system. You have some root directory, right, which is at the very top, the particular drive that we're working in. Then some folders or directories that are stored within that. Then some number of directories or folders within each one, all the way up to some files that are contained within that. Granted, any of them can have files, so any of them can have something that would not have subfolders or other files stored within it, but we can have this branching structure where you have files within files within files. Right. Programming environments, we talked about the fact that Java creates this hierarchical structure by having this is-a relationship. Right? Okay, so let's look at some examples of that so we're on the same page. And it consists of this relationship of parent and child, which we will define. So here's an example of an organogram or organizational chart where you have some organization, computers are us, and within that there are several departments, sales, manufacturing, research and development, and perhaps within that some sub-departments or some small departments contained within that. So for examples, with sales, we have US and international. And within international, you will have groups of employees that are responsible for different areas like Europe, Asia, and Canada. Right. You can think of an organization that's familiar to you, perhaps like Microsoft. You know that they would have within their organization departments that are responsible for different products. There'd certainly be a department that's responsible for operating systems that they create, that have a different department responsible for Xbox, right? Within the department that is responsible for operating systems, you would have sub-departments responsible for the end user versions of those, and then the other ones for server versions of the operating system. All right, so we have a question already. Oh, okay, so there's a question about what we were discussing earlier with hash lists. With the example of uTorrent, would throttling download speed to a user be an acceptable form of punishment, as well as throttling positively for users and as acceptable reward? Well, how do we throttle positively? Understand throttling download speed, right? Making it less as a form of punishment, but how do you throttle positively? Okay, so that's why I answer that. I'll go on. So there's certain terminology that we use, and we should agree on what that is, so we're all on the same page. The root node is a special node within our tree that does not have a parent. So we said that there's this parent-child relationship between the different levels within our hierarchy, but the very first one, which does not have a parent, we call our root, the root of our tree. An internal node is a node that has at least one child, so it isn't one of the nodes that has no children. And our external nodes, which are also called leaves, which I will refer to as leaves or a leaf, are those that have no children. There's some examples of this, but we'll only see that when we actually look at the diagram. An ancestor of a node is its parent, any parents of its parent, or the parent of its parent, and the parent of the parent of the parent. So parent, grandparent, great-grandparent, and so on. A descendant of a node is its child and also its child's children, children's children, which we call grandchildren and great-grandchildren. A subtree is itself also a tree, but it consists of just a particular node and all of its descendants. So in a tree, we could look at a subtree, which we usually say is a subtree rooted at a particular node that contains just that node and all of its descendants, no other nodes, though we may have more nodes in our tree. Well, this also means that a tree is a subtree of itself. I'm sure you've heard about a trivial subset of a set, which is a set itself. The same idea. Look at the whole tree as a subtree of itself as a trivial subtree. We usually look at some smaller collection of elements that are a particular node in all of its descendants. An edge is a pair of nodes, or represented by a pair of nodes, that represents that edge between a parent and its child, or vice versa, right? A node and its child. Then a path will be a sequence of nodes that any two consecutive nodes in a sequence form an edge. So we give a sequence of nodes in such a way that any pair of consecutive nodes must have an edge between it. Right, and there has been answered the question asked before. I guess a new user will have a mid mark that's lower than what the server can accept. Okay, it's max, and maybe through a comma system increases the download speed. Okay, so that could work. Right, and so in a way that means that any person that has that higher one, higher than that mid, would then have a greater, how can we put it? They could be a little too straightforward, but basically they have a higher level, I guess you could put it, within that network. And yes, there are some systems that will then use that combination of some random choice of nodes for vetting, but a random choice of those that have some of the highest rating within the network. So not everybody has to do the vetting. You can actually use the idea that those that have done good work before will have some higher rating, and we'll use that to randomly choose the next person who does the vetting. So then you can use that as well. Right, the idea that you're trying to incentivize people to do correct work. Right, so here's an example of a tree. You'll notice there's only one node that does not have a parent. That would be node A. That would be our root. All right. Then any of the nodes that do not have children, so in this example, we have E, I, J, K, G, H, and D. All of those would be external nodes or leaves. Any of the ones that have at least one child, so A, B, C, D, F, all of those would be our internal nodes. And then a subtree, we have an example here of a subtree rooted at C. So that's C and all of its children. A different subtree would be the subtree rooted at B, which would be B, E, F, I, J, K. Right, so that particular node and all of its descendants. So we want to define our very first idea within this, and that's the depth of a node V in a tree T. So the depth of node V is the number of ancestors of V excluding V. We could define this recursively as if V is the root, then the depth of V is 0. And that makes sense because the root does not have a parent, which means it doesn't have any grandparents and great-grandparents. It has no ancestors, so its depth should be 0. Otherwise, the depth of V is 1 plus the depth of its parent. So think any of the nodes that are the children of the root would then have, well, the number of ancestors including those nodes will be 1. So its depth will be 1. Let's look at our particular tree that we were looking at before. So the depth of A being the root would be 0. The depth of B, C, and D would all be 1. The depth of E, F, G, and H would be 2. And the depth of I, J, and K would be 3. If we look at one example like J, it does indeed have 3 ancestors. So that would be its depth. All right, and then the height of a node is kind of the opposite idea, that if the node is an external node, so if it's a leaf, then its height would be 0. Otherwise, the height of a particular node is 1 plus the maximum height of any of its children. So here, because a node can have several children, then we take the maximum height of any of its children, add 1 to that, and that will give us the height of the particular node that we're looking at. Question, is height similar to breadth? No. Let's look at an example here. So the height of E, I, J, K, G, H, D will all be 0 because those are all external nodes. If we look at F, it has children all of height 0. So 1 plus the maximum would be 1. The height of F would be 1. Then the height of B. B has a child of height 0 and a child of height 1. So we take 1 plus the max of those, which gives us 2. Similarly, on the right, we have that D has a height of 0, C has a height of 1. Then A has 3 different children with heights going from the left to right of 2, 1, and 0. The max of that is 2. So then the height of A would then be 3. Okay, I trust that makes sense to us. So if we want to now define, all right, I'm asked to repeat that again. Let's go back to our example before we talk about the tree ADT. So we'll talk about height this time. By definition, height is if the particular node that we're looking at is an external one, so it has no children, then its height is 0. If the node does have children, then its height is 1 plus the maximum height of any of its children. So we see that for any of the ones that don't have children, their height should be 0, right? We can agree. So for this, all 3 of these 2, and D, there are no children, so all their heights should be 0. We can actually put there next to them that each of them have a height of 0. All of these are 0, 0, 0, 0, 0, and 0. Then we want to figure out the height of our internal nodes. So F has 3 children, all with height 0. So the max of all those zeros is 0. 1 plus that is 1. If we look at B now, B has 1 child of height 0, 1 child of height 1. The max is 1. The height of B is then 2. C has 2 children of height 0. Its height is clearly 1. We look at A then. It has 3 children. Left to right, B has height 2, C has height 1, D has height 0. The max of that is 2. So A has a height of 3. Okay, I trust that makes sense now. We see what those are. Why isn't it 2? Why isn't what 2? Why isn't the height of A 2? Well, what are the heights of its children? 2, 1, and 0. What is the max of those 3? 2. I think we should right away be able to agree on that. And the rule is it's the maximum height plus 1. Granted, in our little algorithm there, we were told 1 plus the maximum height. Once we know what the maximum height is, we simply add 1 to that. That gives us our 3. If we would always just take the maximum height, we'd always end up with 0. Great. And then we have that 1 plus maximum height. So for our ADT, what are the behaviors that we would like? So we could use positions. Our nodes would then implement these positions. A question, why isn't the height of A 4? Well, do any of the children of A have a height of 3? I didn't see that. So it's 1 plus the maximum height of any of its children. Why isn't the height A not 4? 1 plus 2 plus 1. Okay, we can't make up our own definitions. Here's the definition of height. Right, count is defined recursively, but it's 1 plus the maximum height of any child of V, not the sum of the heights of the children of V. Okay, so that's an important issue. Once we agree on what it is, we have to follow that. Great. All right, so back to where we were. The generic methods would be size, which tells us how many nodes or elements stored within those nodes are stored within our tree. Is empty, well, if there are there none or are there some. Elements, which is an iterator, we know what that is. It should return to us a scannable collection of the elements within the tree. Then an iterator position, instead of just returning the elements, return the positions themselves. Then accessor methods, root, which returns to us the position that stores the root, so a reference to root. Parent P, given a particular position within our tree, return the parent of that one. And children P, this will be a position iterator, because now we don't have a single child necessarily, we can have multiple children of P. And so that should return to us some scannable collection of the children of P. Then some query methods for particular positions. Is a particular position internal? Just think you could easily implement that. You would look at its children collection, and if that is not empty, then it's internal. The opposite would be true for is external. Then is root, where you could very easily check is parent of P null. If it is, then you know that it's the root. Right, but just for now, we have those query methods, is internal, is external, and is root for any position. Then the update method, replace P0. So replace now with this new object whatever was stored at position P. So a node is represented by an object storing an element that we used within our list, but now we also store reference to the parent of this particular node and to a sequence of children nodes. These nodes would then implement those positions that we described within our tree ADT. So we could use a linked structure to express our tree, where each of these A, B, C, D, all these would be a node that stores not just a reference to a particular element, but also then a reference to a parent and to a list of children. Right? So what would that look like here? For B, which we saw in our previous diagram, is our root. Its parent one, which is the second little block there, should be storing nothing because there is no parent, right? Then it also has a reference to these children of it. So it has here this iterator that we have here that has references to all the children there. So it allows us to be able to get references to all the children. Each of the children of B, take a look, A, T, and F, will then have a reference to B as its parent. Those that don't have any children, those that are external nodes like A and F, will have, let me just square that, not have any list that or any reference to a list of children, whereas D that does have children will then have a references list, each of which element stores a reference to a particular node within our tree. The other C and E, which are external nodes as well, they have references to whatever elements they're storing, references to the parent D, but then no reference to any list of children. All right, so this is one way that we could store a tree. Then we want to talk about some traversals. Well, now because we don't have a linear structure, as in a single directional order as we had with all our lists, then we could have different ways of traversing all the nodes, all the elements stored within our tree. And there are multiple ways to do this. Question, so we can say that parent is like a header? No, because our header would store no data. Remember, header and trailer were central nodes, they did not store any data. Whereas all we have for parent, the only real exception, is that it does, or rather the root, does not have a parent, so it stores a null reference instead of a parent, but it does store specific data, it does store some element, and it can have multiple children, so it can also have some references to children. All right, so you could say it's like the head rather than header, but even that will be incorrect, right? All of our list head would either have a single reference to the next one in our list, or a reference to that next, and the next would have a reference to it. However, here we don't have that same linear ordering. Each node can have multiple children, which in turn can have multiple children. So there isn't a single linear way that we could traverse the nodes within our list. We could go level by level. We could start at the root and go to the leftmost branch, then the next branch, the next branch. There are multiple ways that we could do this. We now want to investigate some of these traversals. All right. So for the very first one, which is called the pre-order traversal, again, traversal is a systematic way of visiting all the nodes within our tree. For pre-order one, we first visit the current node before we visit any of its descendants. And an application is printing a structured document. Let's look at what a pre-order traversal looks like, then we'll discuss how we could use this to print a document. So the algorithm would be to do a pre-order traversal at V. We first visit V, then for each child of V, we call pre-order on that. What would that do? For each child, would first visit that child, then visit each of its children by calling pre-order on those children. And over and over and over until we don't have any children. So what would that look like? Here we have a tree. We want to do a pre-order traversal of this tree, beginning at the root. So you first visit the root, then visit each of its children. To visit its first child motivations, we first visit that root, visit that node, and then visit its children. So you visit that one, which is now labeled 2 there, then 3, then 4. By convention, we assume that the order really isn't an order, but just the way that we view the children are from left to right. That doesn't have to be the case, but by convention, we do that. So once we visited 2, 3, and 4, we have now visited that node 2. Because we visited, then each of its children. They don't have children, so it ends there. We then go back to 1, because we're actually still busy there. We've only printed or we've only visited one of its children, 2. So the child 1 motivations. We then visit the next child 2 methods. And to visit that, we first visit it, then each of its children. So note it is visited first there as the 5th node we visited, then its children in order 6, 7, and 8. Now we've visited the second child of the root. We then visit its last child, references, and that is visited last. Great question. What does the visit method do? It does whatever we want to do at this particular point, whatever we say is a visit of each node. All right, we'll look at a few examples. At times, we store different things within internal nodes as external nodes. So perhaps we'd do something like print something out for an external node, whereas for an internal node, we could do a calculation. We'll see that that works well for evaluating expressions. In this case, we're trying to print out a document. So for each visit, we could print out what is stored there. So we could imagine that for our internal nodes, that would be make money fast, motivations, methods, and references is not internal. We'd simply make money fast, motivations, and methods. For those, we would store titles and we would print those out. For our leaf nodes, we would have actual bodies of text. And for those, we'd print out those bodies of text. All right? Then a question. Doesn't a tree have only 2 children? No, we have not made that restriction. Each node, and we shouldn't say the tree, each node can have any number of children. Is it a void? Not necessarily. Right, so the visit operation doesn't have to be a void method. So with each node having a visit method, no, it's not that the node has a visit method, it's that we define what a visit should be and we apply that at each node. We'll be calling visits inside visits, allowing us to traverse a general tree. Well, to do a pre-order traversal, we would first visit the current node, then visit its children. Okay. So if we were storing titles and subtitles within our different internal nodes, and then bodies of text within each of our leaves. Then to print this document, we would first print, let's say this was a book, we would first print the title of the book. That would be what's stored at our root. And then each of the children of the root would either be an entire chapter with its title and specific bodies of text, or could be an external node like references, which is simply a list of references. If it's an internal node like One Motivations, we print out what is stored there. So look, because we're doing a pre-audit reversal, we won't simply print all these titles, then all the bodies of text. We'll first visit the root, so we print the title of the book. Then for each of its children, each of its subsections, we visit first that subsection, which prints out its title, then the children of that subsection, which can either be sub-subsections or actual bodies of text. So how to print it out, I would say, make money fast, the title of our document. The first section is motivations, and then within that, there's 1.1 greed and 1.2 activities. Would actually print title, subtitle, and those bodies of text within that. Then we'll move to the second subtitle, methods, print that subtitle, then print each of the bodies of text within that. 2.1 stock fraud, 2.2 Ponzi scheme, 2.3 bank robbery. Then it would print the last child, or want to visit the last child of the root. And so it would visit it, then all of its children, but doesn't have children, so just those references are printed there. All right, now you understand that. Here's some questions. Right, this has been answered. This week's prac, is it going to be trees? I haven't decided yet. I can tell you tomorrow. All right. Can you please explain the visit method again? I'm a bit lost. Okay, I'll do that presently. Would you say a tree is a simple breakdown of something, an activity or a goal? I wouldn't say a tree is simply a breakdown of something. It can be used to represent a hierarchical structure. What that is can be anything. And we'll see as we look at these applications that there are many different things we can do with a tree, because these types of hierarchical structures do come up a lot. All right, then we'll ask to explain the visit method. Well, the visit method can be whatever we want it to be. I'm sure you've looked at a visitor design pattern, but regardless, visit just means do what you're supposed to do at that particular node. And in this case, that doing is printing the text stored at that node. So each element is some text. By visit, we're just printing out that text. For our internal nodes, that text is a title of some sort. For our external nodes, it's a body of text. Right. In other situations, our visit will be something else. So just think, you'll have an actual method that you call. And whatever algorithm you put within that method, that is what will be done. What we're concerned right now is the order in which we do those visits, not what the visit is necessarily. Yes, we looked at an example here, so then we concerned ourselves with what that visit would do, but in general, a pre-audit reversal simply visits a node first, then visits all of its children. For each of those children, its visit is visiting that node, then all of its children. Only then do we return. So we print our root, then to print its leftmost child, we print or visit, maybe more general, we visit that leftmost child, then its children, then return to the root to visit its next child. Right. Question, do we use a visitor design pattern to implement trees? No, we're not going to do that to implement trees, but certainly we're going to do a variation of that to define what a visit should be. As in, we're not really going to worry about what it is until that is done, but we're able to concern ourselves with what we're doing with it, assuming there is some implementation of it. Right? That it will be there when we need it. All right, so that is one type of traversal. Because we're not dealing with a linear data structure, we can have several different orders in which we visit the elements stored within this data structure. One more question. How do we go about getting the reference to a given node starting at the root? All right. That is true as well. Okay, we said that we store here, or rather we have this behavior that you should be able to return the root of any tree, the parent of a particular position, and then the children of a particular position. So if I have a reference to the root, right, or I can return by calling this method a reference to the root, then that means that I can call children on root, which gives me references to all the children of the root. And then I can call children on each of those children and children on each of those children. All right. Each of those gives me a position iterator, so I can use a for each loop to call visit on each of those children. All right, or rather, I'm not calling visit each of those children, I'm calling pre-order traverse on each of those children, which will call visit on the child, and then recursively call pre-order on each of those children. So if you just keep a reference to the root, then that is enough, because having a reference to a particular position can allow you to access its children and its children's children and so forth. Right? And in fact, we can also access the parent, so we can move up in our tree structure as well. So knowing the position of the node is enough. Using root traversal does the rest. Yes, position is like a reference to, granted it has some behavior, but yes, it gives us a way of accessing a particular node. We said in this case, our positions don't just give us element, but also return to us. Let's go back, that's we're on the same page. I'm just making it up. All right. Whatever's implementing it. An example of a node that's implementing that position, it should be able to return to us the element, but also the parent of that particular position, in this case the node, and a sequence of children. So yes, knowing the root would be sufficient to have access to the entire tree, because we're able to then go through our structure. Traversal does the rest. Well, we have to first define what that traversal does. Here we have said exactly how that traversal will go through our tree, but we can have many different ones. And the second one we'll look at is called a post-order traversal. So in this traversal, you don't visit the node itself first, you visit its descendants, then visit it. Then there's a question, what is the big O of traversing through this tree? All right, well, you're visiting all n elements here, so it will be order n. However, there is time spent retrieving those references, and depending on how many times these recursive calls are made, there's also space and time creating those frames that are put on our stack, executed, and then popped off. So in terms of, a better question would be, what is the depth of our recursion? I don't mean the same depth as this, but as in how many recursive calls is the maximum we'll end up with, like how many frames in our stack. That would be, it really depends on how well balanced our tree is and having defined that. But it should be somewhere in the order of log base 2n if it's a balanced tree. We will see that the height, okay, people already started talking about that height, that in worst case, a tree can degenerate into a list. We can actually get a depth of like n minus 1. So just imagine if our tree starts with a root that has a single child, let's say the leftmost child, so a single child. Then that child has a single child. Then that child has a single child. That child has a single child, all the way up to the last node within our tree. Then what we actually have is a list, right? Because there's a single reference from each node to the next. So a tree can degenerate into a list, and you will spend quite some time in the next term looking at how we can have self-balancing trees. So how we can add rules to what should be done when we add a node to make sure that our tree stays balanced, that it actually keeps this tree-like structure. and that we restrict the height in a way to at most log base 2 n plus 1, I believe it is. Right, but we'll get to that. So in terms of analyzing, we'll get to that. Someone says 2 times height or 2 to the power height. No. Then will trees and binary trees be on semester test 1? Yes. Trees generally have less computing time than linear ADTs. Well, some methods on them, yes. And in fact, they lend themselves well, if we're talking about binary trees, to things like binary search. And that makes sense, and we'll see that. However, if we allow the tree to degenerate into a list, then it has the same complexity as a list, or the methods on it have the same complexity as a list, which is not what we want, actually. Right. So in this next traversal, a post-order traversal, the node is visited after its descendants. And an application can be computer space used by files in a directory and its subdirectories. So just think, to be able to tell what the size of everything stored within a particular directory is, you need to know what is the size of the files stored within those subdirectories. And to know that, you first need to know the size of the files stored within their subdirectories going down. So you can actually only calculate that size of the particular node once you know the size of all its children. All right, so that's an application. Let's look at how we'd actually do a post-order traversal, independent of application. The algorithm looks very close to what we had for pre-order traversal, but note, the recursive call of pre-order W, so pre-order in each of the children of V, is done before the visit to V. Right? So we visit V after we've called pre-order on each of its children, which means that we'll actually visit all of the descendants before we visit V. What would that look like on a tree? Well, to do a pre-order on this tree, we call pre-order on its root. To do a pre-order on that root, we first call pre-order on each of its children. So that pre-order is first called on homeworks, which doesn't visit homeworks. It first calls pre-order on each of its children. So on that one in the bottom leftmost node, that one doesn't have any children, so there's nothing to call pre-order on recursively. It simply visits that particular leaf. Note these leaves are just files because they don't have subdirectories, so it calculates what is the size of that file. This pre-order is called on each of the children of homeworks, so each of those has its size calculated. Then we could calculate the size of homeworks. Right? So the visit is first done on the children of homeworks, then done on homeworks. Note, we don't then visit the root. We are still calling pre-order on each of its children. So then pre-order is called on programs, which doesn't visit programs. It first calls pre-order on each of its children. When they're external nodes, it actually visits them. So DDR, stocks, and robot.java, all of those are visited. Then programs is visited. Then the last child of the root is visited, to-do.text, and then lastly, the root itself is visited. So in this one, we first recursively call post order on each of the children, which will recursively call post order on each of those children. Eventually, it visits leaf nodes. Then once it's visited all the children of a particular node, then it visits that node and does so for the children of the parent of this node until it's visited all of them, then visits that parent, and so on until we eventually visit our root. All right, and the example of calculating the size of the space used on a drive is a nice one. To be able to calculate that space for that top level directory, we first need to calculate the space used by each of the subdirectories. We do this recursively until we actually get to files, which are leaves. Those we calculate the size of, and then add all of the children, all the leaf nodes of a particular node to calculate what is the space used by that particular directory. Then moving our way upwards, we're able to then tell what space is used after we've calculated all the subdirectories and files within the top level directory. Then we can calculate the files used by that drive. Right, so that is our post-order traversal. Someone already asked about there can only be 2 children in binary trees. Yes, now we come to the idea of binary trees. So we know exactly what trees are. we can restrict our number of children to create what we call a binary tree. So binary tree is a tree with the following properties. Each internal node has at most 2 children. Doesn't mean it has exactly 2 children, it has at most 2 children. If we say that each one has to have exactly 2 children or 0 children, then that will be a proper binary tree. Right? So all our internal nodes would then have exactly 2 children. Of course, our external nodes would have no children. But here we're saying that it has at max 2 children. So we can have a node with 0 children, which is our external node, 1 child or 2 children, our internal nodes. The children of the node are now an ordered pair, and we can now uniquely refer to each of them as either the left child or the right child. An alternative definition of this would be a recursive one, where a tree consists of a single node, the root, or a tree whose root has an ordered pair of children, each of which is a binary tree. So we can think of it like this. Our tree either has a single node, or it has a single node with 2 binary trees rooted at its children. Then each of those either has a single node, as in their external, or each of them has binary trees rooted at its children. Then those children again are either external, or they have binary trees rooted at their children, and going on and on. Right? If they are a single node, that still counts as a binary tree, or they have trees rooted at each of their children. Apart from the binary trees, do we get other types of trees? Yes, general trees that we spoke of just now. We'll see if the other types are actually the ones that we discuss when we get to balancing trees. They have some rules when it comes to inserting and removing nodes, and depending on those rules, we have different names for those. Right? And not all of those are binary trees. Right. The application of these include arithmetic expressions, we'll take a look at that, decision processes, and searching. Right away, we can see that this would be a great, or rather it lends itself nicely to binary search. If we always store nodes that are, or values that are less than or equal to a particular node on the left subtree of that node, and ones that are greater than it on the right subtree of that node, then to do a binary search would simply check at each node. Are we looking for values greater than or less than this particular value? If we're looking for ones that are greater, then we go to the right child and keep moving down. If we are looking for values that are less than or equal to, then we move to the left child. We could very easily implement a binary search using a binary tree without having to actually calculate a middle node, look at that value, discard half of our list, and then calculate another middle. Here we'll just traverse down either the left branch or the right branch of each node, depending on the value stored at a particular node, until we either find the value that we're looking for, or if we don't find it, we know where we could add it, or that it isn't at all in that tree. Right, so we could use this to calculate arithmetic operations or expressions. We would store at our internal nodes operators, so the ones that we're used to, that we looked at operator precedence about last time, and then we'd store values or operands at our external nodes. What does this look like? Here we have, note, all of our blue internal nodes have operators there. All of our green external nodes have values or operands. Right? So just note, to actually evaluate what is stored, or rather what the result of this expression is, let's say we had what the values of A and B are, we would go down to, so we would do a post-order traversal, that would work for us. If it's a leaf node, we would then return that value. If it is an internal node, we will calculate the result of that operand applied to the that operator applied to the 2 values. So to be able to visit that class would first visit its children. Let's first visit the first child. To be able to visit that multiplier, that multiplication operator would first visit its children. We visit 2, it's a value, we simply return that. We want to now visit the right child. We see that it's actually an internal node. To be able to visit it, we first visit its children. Each of its children will simply return their values. Then we calculate a minus 1. And that's what is returned for that first blue one. Then we calculate 2 multiplied by that, and that's what's returned for the right subtree to the root. The root still doesn't visit itself, it first visits its next child. To visit that multiplication, we first visit its children. Those are external nodes. We return those values. To return or to visit that multiplication operator, we now calculate 3 multiplied by b. That is returned to our root. And then we calculate whatever the result of the left one was plus the result of the right one. Right, so we can store arithmetical expressions within a binary tree, and we can also calculate them doing a post-order traversal. Question, so only a child node without a child will be an operand. Other way around, so an external node, one that does not have any children, will be, oh yes, no, you just say operand, will be a value, and then the ones that are internal, so if there are any children, then it will be an operator. Yes. All right, we can also use them to create decision trees. So to create a decision process, we would then have each of our internal nodes be a question, so a yes or no question. And then depending on what that answer is, you would go to either the left or the right branch of, so to the left child or the right child. Then when you get to an external node, those would hold a particular decision. All right, let's take an example of that. So we have a decision for our first node, our root and internal node. It asks us, do you want a fast meal? Now, depending on what our answer is, let's say it was yes. If it's yes, then we go to the right child of it. If it's no, we go to the left child. We go to the right child. It asks us another question. How about coffee? If our answer is yes, we can go to the right child. Our decision would be Starbucks. If our answer is no, then we go to the right child. Our decision would be Spikes. Right? So each of these would have then a particular decision at its leaf nodes or external nodes. The internal ones would ask us a question. Based on our answer to that question, we'll either go the left child or the right child. And certainly a lot of logic can be represented this way. For those of you doing, let's see, Informatics 3, right now you're working with UML diagrams. Eventually you will get to, let's see, you started with your ones that are representing your use cases. We look at your interaction sequence diagrams. Those are modeled by using links or edges that can depend on a particular decision. So let's say we're trying to do login. If the username and password are correct, you then log that person in. If either username does not exist or the password is incorrect, you tell them and you go back to ask them for the username and password. Right? So there can be more complex versions of this, but you do use that combination of decisions or conditionals and moving to different branches based on that in other types of spaces. Will you do a past paper with us before the test? I don't think we're going to have time because the rest of what we have to cover on trees may well take us to the end of the week. So possibly next week we'd have a bit of time. We could spend a single lecture on that, perhaps on Tuesday, right? But we have to get to the content first, and that willing we will. The only issue, I did mention this before, is that all of the things that you can easily look up in the text, we will not be asking this year, right? Simply because it being an open book test, recall you're not allowed to look at things online, but you do have access to your notes in the text. For us to ask something that you could simply look up would not test your understanding of the content, so we won't do that. And so this semester test will be vastly different to the semester test last year, which was done before universities shut down and was a regular on-campus closed book test. All right, but the part 4 trees are actually were usually application ones. So there are a few questions we could look at that are application ones. All right, that actually brings us to the end of our time. So I will stop there. We'll continue from here tomorrow, and we could finish within that time, and we'll have a bit of time next week, Tuesday. All right, can I upload a mock paper? The answer to that will definitely be a no. And that is based on experience. Last year, a mock paper was given, which was in the same, I would say, vein as the structure of the test, but obviously not the same questions at all. And students then took some issue with the fact that the mock test and the actual test didn't have the same questions. And that's actually what it would be. The mock test would not have any of the questions that would be in the test itself. So all it will do is tell you what the structure would be, and you guys have written tests remotely already. You know what it will be. You'll have an additional hour for upload, and the questions will be simply application questions. So given code, can you, let's say we gave you recursive code, can you create an iterative version of that? Let's say we give you code that has a simple loop. Can you create a recursive version of that? If it's a recursive method, can you do a recursion trace on that? Can you count the primitive operations and give that to us, then the complexity of that algorithm in big O notation? Any of the application things that we've done thus far, we can certainly ask you that, and that's what you should expect. All right, sorry, there are some other questions here. Upload this text. I'm not sure what text you're referring to, but if you mean these notes, yes, those will be uploaded right after the class. So can we say if a binary tree's root has a height of 2, then it's a proper binary tree? No, height and number of children have nothing to do with each other. The height, we haven't really said this yet, but the height of the entire tree will be the height of the root. Remember, the height of each node is simply 1 plus the maximum height of any of its children. Does not depend on the number of children. So it will be the same as our definition for the height of any tree, and it would not be 2. Then, where can you find Eclipse JDK 11 required this Thursday? All right, you can Google it, but if you want, I will just give you a link in what you should do. That is a good question because from this week, if our assistants can't run the code that you give them using what they have, which is called JDK 11, then you won't get those marks. And I should actually note, okay, we're already going to link there where Mr. Marginlop writes for you, so you can go ahead and check it there. One more note is that some of you handed in solutions in .rar format. I allowed the assistant to mark that this week because we hadn't expressly said this, but really you should not have been marked for that because you should know the instructions tell you to upload a .zip file. From this point on, if you don't submit a .zip file, it will not be marked. Because quite frankly, the assistants did have to install WinRAR to be able to extract that, and that should not be required. If you ask for .zip, you must submit .zip. Then, isn't recursion? I'm lost. Yes, a recursive function is one that uses recursion. You shouldn't be lost. And remember, when we were looking at recursion, we discussed a recursion trace, that you can draw a diagram that represents the series of calls and returns that are done by calling a recursive method with a particular argument. All right. Okay, I'm going to stop the recording there.